Hello everyone. In this video we'll be looking into a different impact of crosstalk which will be a delta delay. So what we learned about crosstalk in the past videos was that there was a switching aggressor and it was impacting a victim, and that impact on the victim was in terms of glitch. Okay, it's just like a change in the voltage level. In this case we'll be looking into an impact of crosstalk or the impact of the switching aggressor on the victim in terms of delay. So let's brief about the term that we are talking about here is crosstalk delta delay analysis. So when we say crosstalk, it's basically the impact of switching aggressor on something, on let's say a victim over here. When we say delta delay, so delay is basically a delay of a cell. Delta delay is basically a change in the delay of the cell. So how does crosstalk or the switching aggressor can impact a change in the delay of the cell? This is what the analysis that we are going to do over here, and we'll go also understand the impact of delta delay of crosstalk delta delay. Okay, so let's start with that note. So we have the same scenario. We have the victim driver, we have the victim load, and we have the victim net, and these are the grounded capacitances that we have. Again, we have the aggressor driver, we have the aggressor load, and the aggressor net, and there is again a mutual capacitance that is present between the aggressor net and the victim net, which is shown by the CM, the capacitance CM. So everything remains the same, the circuit remains the same, except the fact that in the previous case, so let's remove all the nomenclatures. Okay, so except the fact that in the previous case your victim was at steady state logic 0 or at steady state logic 1. Okay, but in this case the victim will be not steady state anymore, it will be switching. So in this case the aggressor is always switching, the aggressor was always switching whenever we are doing a crosstalk analysis, but in the previous case the victim was at steady state logic 1 or at steady state logic 0. In this case the victim will be switching. For example, the input of the victim is moving from logic 0 to logic 1. At the same time, the output of the victim will switch from logic 1 to logic 0, and during this period, during this transition period of the victim, we have the aggressor which is switching from logic 0 to logic 1. So while the victim moves from logic 1 to logic 0, the aggressor moves from logic 0 to logic 1, and this leads to something called as delta delay. How? We'll look into that in some time from now, but this is basically a delta delay analysis. Okay, so a few things are pretty clear over here why we call it as a delta delay, or first of all why we call it as a delay. So whenever we say as a delay of a cell, it is basically the midpoint from this this waveform to midpoint of this waveform, that will be the delay of this particular cell. But when crosstalk comes into picture, there is an impact, there is a delta impact on the delay of this particular cell. It could go in either direction, either in the positive direction or in the negative direction, depending upon what is switching at the aggressor. So we'll look into that, all those things. But that's why the reason we call it as delta delay is because there is a impact on the delay of this particular cell. Okay. So now what is happening, as we already talked in the previous videos where we considered the mutual capacitance or the coupling capacitance as a leaky bucket. So when this particular aggressor net or aggressor node is getting charged, or basically when this bucket is getting filled up or getting filled up with water, there is some amount of leakage that happens, and that water gets leaked onto the victim net. And the victim net, the waveform that you see on the victim net, it is supposed to be this thing, but because of the leakage, when it is switching, because of the leakage of this particular bucket, some charges while this node is getting charged, or while this bucket is getting filled up, it fills up the nearby buckets also. So it's something like this. So this will be your buckets, and these buckets are getting discharged, or these buckets are getting emptied, and during that period there is some amount of water that gets flowed through this leaky bucket onto this particular C1 C2s. It's so you see, for some finite amount of time there is an increase in the voltage, or basically there's an increase in the water level, and again after that the same thing happens, the water gets discharged to this particular inverter. So this is a small glitch that you see, but not on a steady state waveform, but on a moving waveform or dynamic waveform. So that's what you see over here. There is a small increase in the bump. There is a bump on the waveform itself. Now the amount of bump that will be present over here, that will be decided on how big is the coupling capacitance and how big is the are the grounded capacitance. So basically it's a ratio. If you see, there is this particular ratio, that is the coupling capacitance ratio, coupling capacitance divided by the grounded capacitance. That ratio will decide the impact of this particular aggressor on this particular victim. So it's pretty obvious. Higher the mutual capacitance, higher the impact, or basically higher the mutual capacitance, more leaky is the bucket, and more amount of water will get flown in this particular bucket. So it's as simple as that. Okay, so this is what will decide the amount of delta delay, or the impact of the aggressor on the victim. So now what we'll do is we'll try to understand how this particular glitch that came on the waveform will impact, and what are the impacts. So we'll try to understand the impacts of Crosstalk delta delay. Okay. So the first impact of the crosstalk delta delay will be, let's try to start with skew. So skew is a very important parameter that we studied, that we'll be studying, or we have already separate set of videos on the skew part, which is the clock skew and clock tree synthesis and all those things. You might want to have a look into those videos. But the direct impact of the crosstalk delta delay will be on this skew, and it's a very huge impact. So let's try to understand what is the impact. So we have this scenario built over here. We have the aggressor net, which is present over here. We had the victim net. The aggressor is switching and the victim is also switching, but during this switching the victim sees that the nearby aggressor is switching, and as a result of that, some amount of charges gets flown from the aggressor node onto the victim node, onto the switching waveform, and as a result of that you see this small bump which is present over here. So now what we'll do is we'll look into a circuit, we'll look into a clock tree. Let's say we have this chip, we have this clock endpoints. Okay, the dots that you see over here are the clock endpoints, and this is the clock source. Okay, when you start tracing the clock from this point till this particular clock endpoint or any of the clock endpoints, you see that latency from the clock source to any of the clock endpoints will be exactly equal. And skew is nothing but the difference in the latencies between two clock endpoints. For example, let's look into an example. Let's say we'll take this particular endpoint. Okay, if you take this particular endpoint, the latency, let us call it as L1, and the latency value will be 1 buffer delay plus 2 buffer delay plus 3 plus 4 plus 5 buffer delays. Okay, it will be 5 buffer delays plus 1 2 3 4 5 6 net delays. So it will be L1 will be 5 buffer delays plus 6 net delays. And let's take any other point on the system. Let's say this one. Okay, when you say this one, let's call it as L2, and the latency of L2 is this particular wire, or let's say 1 2 3 4 5 buffer delays and 1 2 3 4 5 6 net delays. So it will be again 5 buffer delays and 6 net delays. So by the look of it, it looks like the latency L1 is equal to latency L2, and let's put it down over here. And since latencies are equal, skew is nothing but the L1 minus L2, the difference of the latencies, and that will be exactly 0. Okay, so all these terms, latency, skews, and all those things, and the clock tree, the clock endpoints, all those terms are well covered in a separate section which we call it as clock tree synthesis videos. In those videos all these terms will be covered in a very detailed manner. You might want to have a look into that. So now what we'll do is, since we now know the latencies L1 and L2, the values of latencies L1 and L2, now what we have to do is we have to take this circuit and try and understand the impact of this particular glitch on the skew value. So skew is L1 minus L2. We have to somehow show that how this particular glitch impacts this skew. So for that, what we have to do is we have to model this particular waveform, or we have to place this waveform somewhere over here, and assuming that this net is getting affected by crosstalk, and try to compute the latencies again and show an impact on this skew. So what we'll do is, since this will take a bit of understanding and a bit of learning, we'll take this in the next video. In this video we'll try to we'll stop over here with a note that with a note saying that the crosstalk delta delay will have an impact on the skew. How it will impact, we'll look into that in the next video. Thank you.